Welcome back, everybody. So now that we had fun with languages, I love languages, let's go on with back to tokenizing. So what do we do with this? Basically, I showed you how complex it is, how there's a lot of challenges that are in our way of building a system. We have a question in the Zoom chats that received, so I just say a few words. First, it's always fine to ask questions. I know most of you are computer scientists. Some of you are not necessarily. So about ASCII UTF-8, the idea is that when we write as humans, we use letters and characters, but the computers, they only have zeros and ones. So the goal of the encoding is to convert these letters of the alphabet that we use into zeros and ones. ASCII was the first ever encoding in the very early computers. And the idea is that it converted every letter into 8 zeros and ones, which we call bits. And when you have zeros and ones like that, you can see it as a number written in base 2, just like you have 10 digits in base 10, then you have 0 and 1 in base 2. And all you need to do in order to encode in this way is have a catalog, just like you have a catalog on Amazon of many items. You have a catalog of characters, and every character is associated with a number. And then you convert that numbers to zeros and ones. For ASCII, it's very easy, it's straightforward. Every character is 8 bits, and UTF-8 is more like elastic, which allows you to store basically millions of characters and to encode them, but in a way that the simpler one do not take too much space. Does that answer your question on ASCII and UTF-8? Yeah, all right, thank you very much. Never hesitate to ask anything. We are here to learn. And by the way, you know, sometimes you hesitate to ask a question, you feel like, okay, maybe I'm the only one who doesn't know, but very often if you ask, half of the room actually was wondering the same thing. So in fact, you're doing everybody a favor when you ask for a clarification. All right, so now assume we have tokenized, and now you understand it's very hard with Siberian, UPIC, and German to tokenize documents. But we have done that. So now I have these 4 documents. I'm using the colors for the documents and then the rectangles for the tokens. So everything in here is called a token. Every one of these rectangles is called a token. I'm going to remove for the lecture hall this toolbar. There you go. A token is like a coin or something that you can hold in your hand, right? Maybe some of you know it in the context of cryptocurrencies and blockchain, but a token is one of these rectangles right here. And the token is what you get after you tokenize the document. It means you cut it into very small parts, and every one of these small parts is called a token. But we need to distinguish between 2 things. There is the notion of a positional token and a non-positional token. So I'm going to go one by one very carefully to explain all of this. If I take one of these rectangles, I highlighted one of them, it's hour and it's marked in blue. This is basically a token that says the word hour appears in the 2nd position of the blue document, the 3rd document. That is called a positional token, right? Then we have the non-positional token. Here it says that hour appears in the blue documents where we don't know, we forgot. That's what happens with the set of words semantics, for example. This is called a non-positional token. So positional token, you know where you are in the document. Non-positional token, you don't know where you are in the document. For whom is that clear? Okay, these are just the first 2. There are more to come. Now, we have the notion of a non-normalized type. What happened here, it went from blue to black. This is what happens. What it means is we forgot the documents now, right? We don't even mention a specific document or even any specific position. It's just hour. You can call it a word if you want. It's a word, it's hour. Non-normalized means we still see how it's written, the exact form of the verb. For example, at that point, hour and hours would be different non-normalized types. This is called a non-normalized type. In the book, I think they just say type for this, right? But I wanted to make a distinction and explicitly say non-normalized type because there is also the notion of a normalized type, as you might have guessed. So a non-normalized type, this is another non-normalized type. The normalized type means that you group them together. For example, you might have is, are, am, be, been, was, were, and so on and so on. Normalization means you recognize it's all forms of the verb to be. So a normalized type means that you did this grouping and say, okay, this is all the same. It's an equivalence class. So a normalized type is an equivalence class of non-normalized types. It's all the words that belong together because they are just different forms, different conjugations, different genders, different singular plural of the same words. So who understands non-normalized versus normalized? Okay, very good. So just to show it here, if you normalize the two, is becoming be right after the normalization, yes? Just because I picked it from in its form. Now, if you normalize our, it will still be our. But the difference will be that you might also have ours, right? That becomes our as well. So in fact, that's the reason why then I gave this other example, because here it might be less obvious, but here is maybe is more obvious. But I could also have shown be as a non-normalized type, meaning the one that is on the top right there, right? Non-normalized and normalized is really about, did you do the grouping? But it might very well be that before the normalization, the non-normalized form is already kind of the canonical form, right? If you have the infinitive, right? It's all about, did you group it or did you not group it? Yeah, thank you. All right, so now we have four. We have positional token, non-positional token, non-normalized type, non-normalized type, normalized type. And now what did I do? I basically took the normalized type, it's black, there's no documents, and I add back the colors. So now I show them again in the original context, but now it's normalized. How do you see it? The is has been transformed to a b, right? I normalized it. But now if I look at them in the context, there are the colors. There is a blue version of B and a red version of B. And I also have the positions because here I see the order of the documents. These are called positional postings. Posting, because remember, it's both the term in the document in posting. We know the word, the term here, and we know the document that they are in. So these are postings. Positional, because we also have the position. We also know that here we have the normalized type B that is located in the third position of the blue document, document 3, and we have the normalized type B that is located at position 7 of the red document, document 2. For whom does that make sense? Right, so this is a positional posting. Now, as you might imagine, if we have positional postings, we also have non-positional postings, right? Here you go. So the non-positional postings is just that I forget where they are. So I know that B, so the normalized type B appears in the blue document somewhere. I don't know where, but somewhere. And it also appears at some other place in the red document, and I also don't know where. This is called a non-positional posting. And I have this for you. Compliments of the previous year of students, because they really ask for all this classification of things, because that wasn't summarized anywhere. So I did it for you. I prepared this table, and I will again repeat, because this is just the summary of what I said. You have positional tokens, non-positional tokens, positional posting, non-positional posting, non-normalized types, and normalized types, right? Now, how is it classified? There are two axes. First, is it raw or has it been processed, right? When you group, then you process. So this is how you turn a non-normalized type into a normalized type. It becomes from raw to process. Tokens are raw. This is what you really see in the documents. Postings are processed, because this is what you have in the index in the end, right? So raw or processed, that's the third dimension. So 3 of them are raw, 3 of them are processed. Then the second dimension is how do they relate to documents? First, the ones that are not tied anywhere, this is what we call the types, non-normalized or normalized. Then we have those that are tied with a position. These are the positional tokens if it's raw, the positional posting if it has been processed. Then we have those that are tied to a document, but we don't know the position. So these are non-positional tokens if it's non-processed, and non-positional postings after the processing. All right? Now, you already heard the word term. Term is just a synonym for normalized type. Instead of saying normalized type the whole lecture, I just say term. Term is really what you have on the left of the standard inverted index, right? It's a normalized type. And now there is one you already saw before. It is the non-positional posting. The non-positional posting, these are these little rectangles that you have in the postings list. These are in fact non-positional postings, right? So basically the terms and the non-positional postings we already saw last week when we introduced the standard inverted index. Who is that clear? All right, who now would be comfortable with that terminology? Who would become comfortable with that terminology after repeating that for a full hour? Okay, so basically it's clear. It takes a while. Even I sometimes might have a few seconds or to find the right term, but this is the idea. What else do I want to show here? Yes, sometimes, so when you say word, it's implicitly a non-normalized type. A word is whatever you see in a book. The term is the processed version of a word. So word and term can be used as synonyms for non-normalized type and normalized type. Now, if you read the book, that's the last column. This is the reason I put it there. They don't actually say non-normalized type. They always say type. Implicitly, it's non-normalized. And if it's normalized, they say normalized type. When I say posting, it's very often non-positional. You might remember that last week I didn't say non-positional posting, I just said posting. And usually when you just say posting, it's implicitly non-positional. When you say token, it's usually also positional. So if you just say token without precising, you really mean you look at the original document and that's what you get after tokenizing, right? But do not be confused. I put one in gray. I put it on gray because that's not part of that lecture, but you need to be aware that if you took a compiler lecture, what you call a token there is not exactly the same thing. What you call a token in compilers would be closer to a raw non-normalized type, except it's not a human language, it's a programming language. Who took a compiler lecture? Many of you, very good. So don't be confused that we don't call token maybe exactly the same thing in there, because the tokens are actually tied to the documents, which they are not when you use them in compilers. All right. Okay, let's move on then. Okay, still have half an hour. Next, stop words. This is kind of ancient, it lost a bit in popularity, but project yourself back a few decades ago where computing power was limited, and maybe even earlier where we did not even have computers, and humans tried to build the indices manually in a library. So what you do is you basically drop and ignore the common words, like the, a, is, be, like the words that appear so much all the time that they are pretty much in any document. You can take any books. I'm pretty sure if it's written in English, of course, that the word the is going to be in the book. So why bother indexing the, since anyway the posting list will contain all the documents, right? That's the idea of the stop words. So we just typically have lists that circulate that people can use. This is one list that's called the Reuters list. It's a list, I think, of 30 stop words that are, of course, is specific to English because I told you it depends on the language. But these are here, some words in English that are so common that any book you take, the last Dan Brown novel or Joel Dicker, if you are in Switzerland, it's pretty much in there. You will find it in there. Now, the trend is that we used to have large lists because, again, resources are limited. And now it's getting less and less and less to the point of no list at all. In fact, if you use a search engine like Google, I'm not even sure it even has stop words anymore. It optimizes, of course, but there are no stop words anymore. Why? Because we can. We just have the computing resources that allow us to process that, so we do it a bit less. Okay, but nevertheless, that's good to know for historical reasons. Okay. Next, normalized types. I should even have said normalized in the parentheses. So the equivalence classes, this is the notion of processing. When I told you the difference between a non-normalized type and a normalized type, it's the idea that you put together what is just a different form of the same thing. USA with dots, without dots, today, the 19th century, if you have old books today, Zurich, Zurich, and so on. So it's all the same city. Windows with a capital W. And here you start seeing the limits, by the way, because Windows, is it really the same if it's the operating system as window? Maybe not, right? So again, you see it's not so trivial. But if you forget about the operating system, it's kind of the same equivalence class, right? Uppercase, lowercase, and so on. So each one of the small, the words you see in here, they are you could consider them non-normalized types, and the big circles containing the groups, these are the normalized types. What you do very often is that instead of looking at the circle, you take one of the words inside and say, this is the canonical one. For example, instead of referring to the whole circle, you take this one and say, okay, that's the canonical one. Maybe you take this one as the canonical one, maybe this one, and maybe, yeah, let's take this one as the canonical one, okay? In fact, you do the same in mathematics. You know, when you probably took discrete mathematics and you have the modulo n, for example, you have the equivalence classes of the remainder with the division, the Euclidean division by n. But instead of saying, for example, if you do it in the binary form, you divide by 2. You have 2 equivalence classes. You have the odd numbers and the even numbers, right? But you don't say, for example, if you do arithmetics with this, you don't say, I'm adding the even numbers to the odd numbers and I find an odd number. You don't say that. What you say instead is 0 plus 1 equals 1, for example. And what you've done here is that for the odd numbers, you took a representative, 1, and for the even numbers, you took a representative, 0. And then you do everything writing 1 and 0. But implicitly, 1 and 0 are not the actual 1 and 0. They are representative of the whole even or odd numbers. It's the same here, right? So we kind of identify the whole class, the whole normalized type with one of the non-normalized type, which allows me to circle back to the question you asked earlier about B, like why our is shown and you say it's a non-normalized type. Because if our is really the non-normalized version, that would be any of the words in the circle. But if you take our of the representative of the whole circle of the other words that look the same, then word becomes a normalized type when you do that. Okay? Who is following? Who is lost? Okay. So how do we normalize then? Because you could look at the whole document and group together what belongs together. In fact, now that we are in 2024, you might be thinking in your head, clustering, machine learning. Some of you, who is thinking word embeddings, large language models when you see that? Some of you, right? So you see, you already have the 2024 mindset when you do this. But it didn't start that way. We didn't have that luxury historically. So what happened is that instead, do we have a question?
Yeah, there's a question. Is the Reuters list also called the stop list?
The stop list?
Yeah.
It might be that I would need to check if casually people might call it in this way. We'll come back to you if we take a note. Yeah. Okay. All right. So how do we do it without? You're welcome. How do we do it without word embeddings? So you can have, heuristics. Like, for example, you remove the dots, today, you remove the dash, and so on. So you can have a rule-based approach. Yes? Kind of, but not quite. In the sense that, yep.
Opposite things, but have the same word. Like you said with window or Chicago, which is the back as well. How would you do that?
Mm-hmm. So here you need to distinguish between two different ways of grouping. If you consider, I have a few examples actually coming with techniques, but for example, let's say lift and elevator, right? Lift and elevator, you could kind of put them together, right? But that's not, it wouldn't be considered a normalization in this way. Normalization is really based on the rules of a language that it's the same family of words grammatically. Like, you know, there, then, them, words that basically relate together grammatically, but you wouldn't put synonyms in the same group when you do that. But it still makes sense to put synonyms in the same group in different contexts, right? Like, for example, I will show you the index expansion. In the case of large language models and word embeddings, you do put synonyms also together. You just need to have in mind if yes or no, do you consider synonyms to be the same, or do you just stick to grammatical equivalence, right? But it is something to be aware of course, of what you are doing. Okay, all right. Okay. Now, coming back to this Windows thing, is it the same thing? Is it not the same thing? Now, okay, coming back to the large language models, in a large language model with attention, you probably can know if you're referring to the operating system or not, depending on the context. But again, imagine you don't have that. Then what you could come up with is some rules. Like if it's a capital W, uppercase W, you keep it that way and that's it. Windows, you expand it to Windows, also capital W, window, and so on. And the lowercase window, you expand it to Windows. But now you're going to tell me that's completely different, right? Because here I showed you that we are grouping together the non-normalized types into normalized types. But now what we are doing here is completely different. Why? Because that's not an equivalence relation anymore, right? You remember what an equivalence relation is? It's a relation, we try to get it on the top of my mind, it's a relation that is transitive, symmetric, and it's like the Siebenbundesräte, there's always one you never get immediately. So symmetric, transitive, and reflexive, right? So if it's symmetric, transitive, reflexive, it's an equivalence class. Here, it's not symmetric, right? Because you go, for example, from Windows to Windows with a capital W, but not back. So this is not an equivalence relation anymore. So that's something different. We can no longer say it's normalized types as we do here. Here, we can no longer talk about normalized types in any way. It's asymmetric. Instead, we call it expansion. We expand. And that is when we can do it with synonyms and like lift and elevator. I told you I had a slide with that. Since it's not symmetric anymore and we can no longer normalize with normalized types, we do it differently. So how do we do that? We basically have two ways of dealing with asymmetry: index expansion or query expansion. So the idea of index expansion is that I build the index, ignoring that there are synonyms. I might find this. So maybe this is lift is in Great Britain, in the UK, and elevator in the US, right? Is it the opposite? Can't remember. Anyway, so 1 and 5 have the word lift, and 1, 4, 6 have the word elevator. And expanding means you're adding the other postings to the first one. So lift, for example, is expanded with all of these. Sorry, with all of these, and elevator is expanded with all of these. Now you end up with lift in 1, 4, 5, 6. But knowing that 4 and 6 is not that it was a direct occurrence, it's that it's a synonym occurrence, that it's actually elevator, but you do want it in the index, right? So this is what happens. This is one way. And then if somebody queries for lift, you look it up in the index, and you have here the postings corresponding to lift, but it will also include elevator because of this expansion. Or you don't expand the index, keep the index like this, but you expand the query instead. Now you have lift, and you modify the query, and it becomes lift or elevator. And now you have lift or elevator. This you know how to do. You do the union of the postings lists as we did last time, and you get the same results, in fact, right? So either index expansion or query expansion. For whom does that make sense? Right? Who sees that it's because it's asymmetric that we have to do this, right? If it were symmetric, we wouldn't need that. We would just merge and use the normalized types. It would be the same term in the... All right. Now, which one do you pick? When you have to reason a little bit like when you run programs, computer programs, what you do at compile time and what you do at runtime. The index expansion, you think of it at compile time. it's basically before the system is launched, you expand the index, you do it just once, but it takes more space, but it's going to be faster. Or you don't pre-process, so you just launch your system with the original index, and you expand the query. The index takes less space, but querying is going to take longer. Why? Because every time a user comes with a query, you need to expand it, right? So on the left, it's a compile time thing. On the right, it's a runtime thing. Who sees that? Okay. Okay. Now, other aspects can be the accents, like you might remove the accents, or even, you see, by language is complicated. The umlaut is replaced typically with an E. At least in High German, in Swiss German, it's different. Like Gut is not the same as Gut, maybe Gut in Wallis, but it's not as simple as in German. But you have these rules. Then you have maybe lower casing like this, and so on. Then there is something else called true casing that I know nothing about except that it exists. But with machine learning, you can figure out it in this way. And probably nowadays, that's even using attention and word embeddings that you can do these things, right? Okay. All right. So this is normalization. But there is something in English that works remarkably well, and that is extremely popular. It's called stemming. These rules here are a bit arbitrary, right? How do you come up with them? A stemmer is basically a systematic way of building rules. It means that you have rules that remove typically the suffixes of the words. So analysis becomes analysis, feature becomes feature without an E, and so on. So of course, what you have on the right is not even English anymore, but these are your normalized types, right? How do you do that? With rules. One famous set of rules is called the Porter stemmer. There are others, but the Porter stemmer is very famous. It's just mechanical. You have a set of rules that tell you whenever you see this, you can replace it like this. It's actually relatively efficient. You can do it on old machines as well. And that turns any English word into a normalized type. It's not English anymore, but again, it allows you to group together to get the terms. Porter is one of them. So this is, you have the original document on the top in bold. Then you have the Porter version. So you see the normalized types that you get with the Porter stemmer. Then you have the Lovins stemmer that does it differently, and the Pace stemmer. Okay, so these are different ones, and I think the Porter stemmer is the most famous one, but each one has advantages and drawbacks. All right, so a stemmer is just a set of rules that takes care of this normalization, right? Of normalizing the non-normalized types into normalized types. And again, it looks like this. If you look, you can download it. I'm pretty sure if you type it under Google, you will find this list of rules, right? And you can easily write computer programs that apply these rules. But there is a disadvantage. It only works in English. If you put something in French or any other language, that's not going to work. This is really highly specific to the English language. So there is another approach, because that's working well with English. What do we do with other languages? Let's say German, Spanish, Italian, French, the ones that basically have all of these conjugations, right? Here it's a bit more complex, and that's typically the thinking of translation. How do you translate a text into another language? And here you can think of it in this triangle that basically goes from the left to the right in terms of translating things. And the interlingua was the holy grail of this whole thing of finding some kind of universal language that covers everything. And you just gain in abstraction when you go up, right? So the idea, when you use lemmatization, it's not like the Porter stemmer, is that you really take into account the grammar of the language and more precisely the morphology of the words. So in that case, you would kind of know that computer, compute, computes, computed, computation, computing, this all goes together, right? But it's not rule-based like the stemmer, the Porter stemmer. It's really based on the actual knowledge of the language. So typically in English, it doesn't help that much, and the Porter stemmer is more efficient. But when you have other languages that do have all these conjugation rules that actually becomes a better approach to use lemmatization. Who is with me? Okay. So to summarize, when you try to account for the fact that the words can have different forms, you have a symmetric approach and an asymmetric approach. The symmetric approach is based on equivalence classes of words. You can use two techniques to build them: stemming and lemmatization. Stemming is mechanical rules, like the Porter stemmer, works well in English, probably also in Swedish, Chinese, like all those that don't have complex conjugation. And lemmatization is when you use the grammar rule, you're aware of declination, you're aware of conjugation, and so on and so on. That's very good for languages like German, Italian, French, Spanish, Hindi, and so on. Okay. All right. So that's for the symmetric. And then you have the asymmetric approach, where it's no longer an equivalence class, so you can no longer talk about normalized types anymore. But then what you use is instead expansion. You either expand the query at compile time, or you expand the index at compile time, or you expand the query at runtime. That's the summary. Okay. So now let's go back to some optimization, kind of slightly different parentheses, skip list. Remember that we built this. It's an inverted index. You see in purple the document frequencies, and then in blue, yellow, green, red, the postings lists. So you see in gray, you have now, you know that these are terms. These are normalized types. You know that the rectangles, not the purple ones, but the others, these are all non-positional postings. Right? These are all non-positional postings. And these are the document frequencies. We'll talk more about document frequencies in a few weeks. But this is a standard inverted index. Now, you know how to implement AND and OR with union or intersection of this. So this, for example, was an intersection algorithm that we used. Who remembers how to do union intersection? Okay, you traverse the two lists concurrently, right? And then you spit out the postings below. Okay, let's do it again then, but on a different example. So you remember the algorithm for the intersection. So I start here. 1, 1 is the same, so I output it. Then 2 is smaller than 1, so I just move. 3 is the same, so I output it, then I move. 4 is smaller than 10. So I move by 1. 5 smaller than 10. I move by 1. 5, 6 is smaller than 10. So I move by 1. 7 is smaller than 10. So I move by 1. 8 smaller than 10. So I move by 1. 9 smaller than 10. So I move by 1. Oh, now 10. I output it. Then 11, 12. I moved both by 1 because it was a match. 12, 12, and so on. Now, did you notice anything here? Something a bit inefficient? Yes? Do you mean after we arrive at 12? Or yeah. Yes, this is one way that you might have. I'm thinking out loud, if you could try to optimize that you can end early. It's not what I wanted to illustrate, but I could imagine that you could also try to find optimizations. In fact, I think, no, what I'm telling you actually, what I'm going to show you would also help with what you say. It would also help you with optimizing that case. Here you see there's only the 14 left, but imagine that after the 14, there's like 100 higher numbers. Then yes, you're right, that can be optimized, right? Did you see something else? Then I'll explain. Yes? Yeah, you see, I kept advancing here, but nothing actually happens. That is inefficient. Imagine if it's like 1,000 times that it happens. Just so that you imagine that A is a stop word. You remember a stop word would be basically a very long posting list because it's everywhere. And B is a very rare word, right? Like Donau, Schiffer, blah, blah, blah. And it appears only in the world of records, for example. Then in that case, that's going to be highly inefficient. You're going to basically be walking down the list of the stop words forever without ever splitting anything. So this is why we have a solution for this. We need to move. How could we make this faster? Imagine that we are at Hogwarts and we have these magical things that we can do. So imagine that we had a magical pointer, right? I have magical Fourier, bam, I have this magical pointer. And that pointer just tells me, okay, I know that if I jump there, it's going to be 10, and everything before that is less than 10. Do you see that with this magical pointer, I don't even need to traverse anymore between 4 and 10? Who sees that? Okay, so I can just traverse the pointer, look into the future, right? And then see, it's like with these magical glasses, was it in Minority Report? At some point there or Paycheck, can't remember, there's these magical glasses to see into the future. So imagine we have these glasses, we see, you see now I can magically directly jump in there because I know that there's going to be nothing in between. Well, it turns out that we can in fact implement these pointers. And these are called skip pointers. So in practice, this is how it would look like. We basically know that we can jump directly to 4, directly to 7, directly to 10, and so on. So I have a question for you then. How do you think we should go ahead and implement these pointers? Like how many of them, how long should they be, and so on and so on. So first, let me check that the page, I need to, yes, okay. Share screen. There you go. So tell me, what do you think should be the ideal size for one of these skip pointers? Answer A, 42 always. Answer B, the square root of the number of documents or the number of postings. It's the same thing, non-positional postings. The logarithm of the number of terms, which are the normalized types, the terms, or the square root of the length of the current postings lists. What do you think? Aha, logarithm of the number of terms or the square root of the length of the current posting list. And the majority wins. And I see there are some Hitchhiker's Guide fans here. All right. The problem with 42 is that it takes 1,000,000 years. So that's probably not the optimal way of implementing it. All right. Normally, I click here, we should land back to where we were, if I got it right. Yes. So in practice, we don't want too short pointers because otherwise you're not optimizing anything. Plus, it's a waste of space. But you also don't want too long skips because then you never get to use them. And that's not really useful. So you want something in between. And so the ground rule is you just take the square root of the posting list size. For example, if there are 16 postings, you take 4 times 4, 4 skip pointers of each a size of 4. If it's 100, then 10 times 10, and so on and so on, right? For whom does that make sense? That's the kind of the compromise. Okay. How much time do I still have? 5 minutes? Do you want to go for lunch, or do you want me to tell you a bit about phrase search? Who wants to go for lunch? Higher, just so that I see. Who does not want to go for lunch yet? I think there's more people who want to go for lunch. So I just have a few more slides here about phrase search. I'll tell you about by word indices and about the indices with positional postings, how they look like. Just before you go, I just want to make sure that you followed me and then you're good to go. So this is my accelerate or slow down question. All right, perfect. My goal is to have between 80 and 99. Basically, if everybody understands, I accelerate. And if everybody is lost, then I stop. Don't worry if you are between 50 and 75 or less than half, there is the book. You can read the book. You have a whole TA team at your service and also me to help you, right? So we are here to help. Thank you very much, everybody. Enjoy your meal and enjoy the exercises too about the Boolean engine, and see you next week at 10 a.m. Thank you.